Hi Aniruddhan.
Hi, Bobby.
So last class, what did we do? Towards the end of the class, we were working with some capacitor.
That's right. That's
It
right.
charged, and then some representation of that in S domain
In
was
S
there.
domain.
So at that time, we used, I think, I is equal to C dV by dt. But capacitor is mostly, I mean, we also remember the expression
1 by
1
C
by Z integral I dt.
I dt. Correct.
So suppose if one chooses to use that,
Okay.
there should be
The answer, you should get the same answer.
correct.
You should be able to proceed with that also.
Correct. Or in general, if I have, let's say, some signal, f of t, I am integrating from, let's say, 0 to t dt. I want to find out Laplace transform of this.
Okay.
How will I go about? Normal equation we can.
We'll apply the definition of Laplace
Yes.
transform.
Yes. So that's integral 0 minus 2 infinite. Integral 0 to t f of t e power minus st dt.
I think, do you need one more dt here?
Correct.
Because you have two integrals.
Yes.
Okay, yeah.
Because that's the one we wanted to find out.
Correct.
So what we will do now? UV method.
Let's do that.
So this shall be u.
U.
So then we want du, no?
Yes.
Du is f of t dt.
F of t. Yeah, f of t dt.
And this is dv.
dv.
So this means v will be e power minus st by
I think by s.
by
Isn't it? Oh, by minus s.
minus
no?
s.
Yes. Correct.
No? So now we can do integration by parts. What's that? uv minus integral v du.
V du. Correct. That's what we need to find.
U is f of t, sorry, integral 0 to t f of t dt.
Correct.
V is e raised to minus st by s.
By minus s.
Minus s.
Yes.
0 minus 2 infinity.
Correct.
Minus
v du, no?
v.
So e power.
So this is 0 minus 2
infinity.
v du.
Yes. So e power minus st by s.
st by s.
Yes.
dt.
F of t dt.
Yeah. v du.
Correct.
Okay, maybe here we will apply a limit.
Yes. Here let's apply the limit. So at infinity, e power minus st should be 0, no?
Yeah. So that way that is 0.
Correct.
Then minus, we are integrating from 0 to 0.
Okay.
When we give
Correct.
time t equal to
Correct.
0. So that will be 0.
That is also 0.
Okay.
Understood. Okay.
Minus 0 minus 2 infinity. I will take that. Oh, this was minus s, no?
No, that was minus s. Correct.
1 by s plus.
Correct. Oh, I recognize this. You've seen it many times before.
Yeah. So this is f of s itself.
Correct. Oh.
So that means f of s by S.
Perfect.
So now if you compare with the differentiation, there it was
S times f of
yes,
s.
f of s.
Correct? Okay.
And
Oh,
here
I
it
see.
is. So
Nice. So anytime we are interested in the integral
of an f of t,
of an f of t, then we can use this property.
transform it and divide by s.
Correct. Transform it and divide by s. I think it will be very useful for inductors and capacitors, where you can write the current voltage relationship as either differential or integral.
Okay, okay. So that means if we have circuits with capacitor, we should be able to find a solution
Correct.
using Laplace transform.
Using Laplace transform.
We'll pick some example.
Sure, sure.
So I have some example. Let me. So I have a u of t. Then 4 ohm resistor. From there a capacitor. Just simple RC circuit. Its value is 1 by 16 farad.
Farad. Okay.
Large capacitor. And across this I have V of t. Actually V of 0 minus is 9 volt.
Okay.
This is what it is given.
Okay.
Question is how do you get I of t?
Okay. So this is like if you have a voltage source u of t, it is like a 1 volt voltage source in series with a switch.
Correct.
That is thrown at t equal to 0.
Correct.
It is equivalent
Correct.
to that.
Correct.
Okay.
Actually, we have done one RL. Sometime.
Exactly. There we explicitly drew the switch, I think. Did we? Or did we give u of t?
I think it was similar.
It was just similar.
Yeah, it was also
okay.
u of t.
Okay.
So first we'll write the
Time domain
equation and then try.
Yes, let's do that.
So time domain equation. So what we are saying is we have 4 I of t plus
so
1 by c integral
1 by
ID,
c
no?
integral I dt.
So 1 by 16
1 by 1 by
1
16.
by 16,
So 16
that will become 16 integral I of t dt.
dt. Yes.
So the capacitor had a charge
Correct.
0 minus.
Correct.
So maybe as a general equation, it can be from minus infinity to
Correct.
any time t.
Correct. Because that v of 0 minus, you need to integrate from minus infinity to 0 minus to find out the initial charge.
Correct. Correct.
Right? So this is correct.
Correct. So this is equal to u of t.
Yes. Correct. This is just KVL around the loop.
Correct. Now, how will I bring in this guy there? We will split that integration.
That's a good idea.
So that means 4 I of t plus 16 minus infinity to
0 minus. 0 minus or 0, which is a good or the correct way of representing?
Maybe 0.
0. So at time t equal to 0, we are looking at the
correct
charge.
Correct.
Okay.
T dt. Then I have. So this can be 0. Yeah.
I think it won't be a.
You mean 0 minus is precise, huh?
0 minus may be precise because just before u of t comes in is what we are giving the charge. But yeah, so I think 0 minus may be even more precise.
So here also.
0 minus to infinity. T. 0 minus to t. I of t dt. Correct.
Okay. Now what you are saying is for this we have some value.
Correct.
That is v of 0.
That is v of 0 minus.
So this is 4 I of t plus b of 0 minus plus integral 0 to t I of t dt equal to u of t.
Correct.
Okay, now if we have some equation like this, we should be able to
Solve it.
or
So
represent in S domain.
S domain. So basically what we'll do, we'll just take the Laplace transform on both sides.
Okay, okay.
And that will give us the S domain.
So let's try.
Let's try it out.
So the Laplace transform will be 4 I of s.
Yes.
Then this is a
It's a
DC
fixed
board.
value, so
Yeah.
it will be the same, right? But
4 by s.
by S,
Correct.
that's right.
Correct.
Correct.
And maybe we can supply the value also 9. I mean,
Correct.
because it's given 9.
It's given 9. So we can just write it as 9 by S.
Okay, then here what should I do?
Mm,
So what we learned just now is
ah,
if we have integral 0 to t f of t dt, it is f of s by s.
yes. So here we'll have 1 over S I of S.
I of s.
Correct.
Did we miss anything here in this process? I think I missed 116.
16. So 16 by, this is just 16 by S I of S.
Correct. So
Correct.
there is a 16 here.
For the second integral, that is right. Correct.
16, 16.
Correct.
So this is equal to 1 by s.
U of t is 1 by S
1 by
also.
s.
Correct.
So I'll just rewrite it.
Yes.
I of s. I have 4 here, then 16 by s equal to 1 by s minus 9 by s, which is minus 8 by s.
Minus 8 by S. Correct.
Or I of s is equal to minus 8 by s divided by 4s plus 16 by s.
By S.
S and S will get cancelled. We can divide by 4 also.
So yes. So minus 2 by S plus 4.
So minus 2 by S plus 4. Also this is I of S.
Correct.
Now we need to go back to time domain.
That's right. Didn't we see a rule where we got something with the Laplace transform 1 by S plus A? I think let's maybe.
So 1 by S plus A.
Correct. Didn't we get?
We got something like that.
I think the one that
Shall
had
I-
it was.
shall
Yeah,
I-
let's scroll.
So in fact we have used here.
We have used it there. So students are already familiar with it. E
So
power
it's-
minus AT
Okay. E
Right.
power minus at U of t.
U of t.
Yeah.
E power minus AT U of t has this. Correct.
Okay. So that means our
Current.
answer
Yes. So
I of t is minus 2 e power
minus 4t.
4t. Correct?
Yes, correct. Perfect. So technically, because
U of t.
like you said,
Ah.
e power minus AT U of t is the one that has 1 by S plus A.
Hmm.
Because functions of time can be valid both negative and positive times. Here we are turning on the voltage source only at t equal to 0.
Correct.
So there can be no current before that. So we are just assuming that we have to use this U of t. Correct? Is that right?
Yeah. So this many amperes.
This many amperes.
Yeah.
Correct.
So this is an exponentially decaying current. And finally it will be 0.
It will be finally 0. Correct.
Why is it negative? Oh, because this is only
Yes.
1.
1 volt. The
And
initial charge
initial
was
charge is 9 volt.
9 volts. So the capacitor is charging the voltage source.
Hmm.
Ah, okay.
So the current is flowing actually in the opposite
in
direction.
the opposite direction. Okay, okay.
Oh, this is good. But
Actually, we would have seen this
Hmm.
if I think we saw that the capacitance can be represented. Did we see some representation of the capacitor?
so you mean this one?
Something like this. But this was in the Laplace domain,
Correct.
right?
So we should be able to use this and then solve also.
Use this and solve also.
Let's try that.
That's why suddenly when you said 9 volts and 1 volts,
Correct.
I thought we should try to use this also.
Yeah. So just for the sake of saving memory, I will copy this.
Sure.
So we'll do it in a fresh page.
Yes.
So we have this information, and then this circuit we actually wanted to solve.
We can copy this
I'll
also.
copy that also. So what you are saying is, instead of writing these equations,
Mhm.
can we,
Solve it just by
In-
using that.
like we have done for the inductor?
Correct.
Oh. Okay, whatever I copied is gone, I think. I'll copy once again. So how to represent this in S domain directly?
Correct.
So anyway, we have the source 1 by
1
S,
by S. Correct.
then resistor as it is.
As it is, 4 ohms.
Then comes the capacitor.
Correct.
So we have the capacitor and then some series
Correct.
voltage, minus plus in this direction.
Correct.
And this is 1 by CS,
Correct.
which is 16 by S,
16 by S.
and this is minus
Minus
V0
V0.
by S. So I can change the polarity here.
You can change the polarity there.
Plus minus
V of 0 minus is 9 volts.
9.
9 by S.
Okay. So I of S I should be able to write directly. Is equal to total voltage available is 1 by S minus
9 by S. So minus 8 by S.
minus 8 by S. Total impedance of
Impedance is 4 plus 16 by S.
okay. So that is minus 8 by
4S plus 16.
which is
Correct. So minus 2 by S plus 4, no?
correct. Did we get the same
Let's see.
value?
I think we did. Minus 2 by S plus 4.
Yeah.
Oh, perfect.
Okay.
So this is much easier.
Yeah.
Much
Just one
faster.
step.
No differential equations, no
Yeah.
integrals, nothing.
Yeah.
Algebraic equation.
I don't have to think about these things.
Correct.
Minus infinity to 0, minus what's the voltage. I mean, all these are taken care automatically.
Correct. And once you know I of S, you just need to find out what I of T is.
Yes. So just the sake for completion, I of t is minus 2 e power minus 4t u of t
Amperes.
amperes.
Perfect.
Okay. So this looks very easy.
Yes.
So what shall we do now?
Maybe shall we try to summarize this?
Yeah, because
Because you have learnt an inductor equivalent circuit,
correct.
capacitor equivalent circuit.
Yeah,
Maybe we should just summarize it.
we'll do it in a fresh
Yes.
page.
Yes.
So what you are saying is we have some elements in time domain,
Correct.
or I'll just write time domain because this is not f of t, no?
This is not f of t. You can just say time domain.
And then we have corresponding thing in
S domain.
S domain.
So we have two, no? One is series equivalent, the other is parallel equivalent.
Okay. So I'll
So you can just say S domain,
yeah,
and just have two columns.
yeah. So first is of course resistor.
Yes.
You have current I of t, resistor R, V of t. Here, I mean, there is no,
There is no problem.
so I can just write it as I of S and resistor R.
Yes. Yes.
We leave it there.
We'll leave it there. It is only the inductor and the capacitor that have a
There is
series and
some
parallel.
initial condition that can
Correct.
come.
Correct.
So next is inductor.
Yes.
Let's say, sorry, I of t. And we have value L. Voltage across it is V of t.
And initial condition.
I
Some
of
I of 0
0
minus.
Where will I write that?
So write down next to it, no? I
Yeah.
of 0 minus.
If it has.
If it has.
And this I of t is L di by dt. Just to recollect that we have to use the.
That is right.
Okay. And then what we had? We had one inductor and a current source. Huh?
In parallel. Correct.
This was upward, downwards?
Downwards, I think.
Okay. We
I'm
can
trying
cross
to
check.
remember. We can cross check, yeah. Let's go back. I think for the inductor, it might have been upwards. Let's just confirm it. We didn't draw the parallel equivalent, but
we'll just copy this.
depending on the sign. So
Yeah.
unfortunately, depending on whether you use a minus I or a plus I, it can be
Direction
downwards.
can
The
change.
direction can change.
Correct.
Right. So I know I thought we had done it for the inductor also, but we will.
So what we have is this.
Yes.
Then maybe
Correct.
then maybe we'll draw that first.
Yes. So we'll draw it on the right side here.
Yeah.
The series equivalent.
So V of S is a voltage across
Across the inductor. Correct.
inductor. This was SL.
Correct.
This was plus minus L I of 0 minus.
Correct. Correct.
Or I can write it as
So that is why I was
plus
thinking,
and then-
exactly, then it
yeah.
will change. So which is why maybe your initial instinct to put an upwards arrow may be better. The upwards arrow, if you do, it's negative. The upward current will be minus
correct.
negative.
Yeah.
The downward one will be positive.
Yeah.
Depending on which one you want to use.
So this will be upward
Minus L times I of 0 minus divided by SL.
So that means I of 0 minus
By S.
by S.
Yes. or a downwards current which is I of 0 minus by S.
Correct.
It doesn't, both are equivalent.
Correct. And this is
SL.
SL.
This is like a source transformation.
Correct. If you want to write it as Y of S, then it has to be 1 by.
It has to be 1 by.
Because some textbooks I've seen they write it like that.
Because when they do parallel, they do
Parallel.
Y. I think unless you say Y, it normally refers to the impedance.
Yeah. So this looks okay.
This looks okay.
This I can raise. Okay, now we'll bring in the capacitor. And so here should we keep I of 0 minus or V of 0?
V of 0 minus.
That will
That's
be
a
better.
normal way of, we'll just say V of 0 minus.
Yeah. So this will also be available.
Correct. And shall we also write the expression in the time domain?
Yeah.
We want to write it as 1 by C integral, C dV by dt.
Yeah.
Oh, by the way, I think this is V of t equals L di by dt.
Correct.
I think we should correct
Sorry,
that as
sorry,
well.
sorry.
I just noticed it.
Thank you. I'll use a different color. Here we'll write
We'll just write it there.
V of t is L di by dt.
Yes.
Yeah.
Same way we can write it at the bottom. I of t is C dV by dt.
Yeah.
I think we also taught in class the series equivalent,
Series equivalent.
right?
I think we have done both.
We have done both for the capacitor.
Let
I
me
think
see.
you're right. We've already done both. Yes, we
Yeah,
did both for the
yeah.
capacitor. So we'll write it.
So this was 1 by CS
1 by Cs
and this was
minus plus
Yes.
and minus V of 0 minus by S. Yes.
yeah. Again, it's up to the person to use the polarity, no?
Correct.
Because it's 2 times minus is seems
I know.
unnecessary.
So you can change it now. You can change
We'll
it
change
right
it?
now. We'll change it right now.
So I can make it plus and inside also change.
Correct.
Plus minus.
Yes.
So now the parallel model, okay, here it is I of S. This is V of 0 by S by,
By
1 by
this.
CS.
So C times V of 0 minus.
This is 1 by CS itself.
Yes.
So actually, if you remember this, that is enough, no?
That is enough.
I can always do source conversion and
Correct. You only need to know one of them.
okay, nice.